Earlier, when discussing essential boundary conditions, we saw that we can calculate the heat flux going through the left boundary, and that's a boundary at which we have our temperature or essential boundary condition. And at this point, I know the temperature at node 1. That's anyway known from the boundary condition. I know temperature at node 2. So I can back out what that heat flux is. And that times, the heat flux times the area would be what ANSYS would report as a reaction. And if I plug in the numbers, I get that the flux at that boundary is minus 5.5 watts per meter squared. And I picked K to be 1 in SI units, so dt dx is just the negative of that, and that's 5.5. And it turns out it matches exactly with what you get from the exact solution. The implication is that the reaction that I calculate matches, so it's getting Q out exactly right. And that's times area is the amount of heat going out through there. The amount of heat going in is Q in times A, and that's specified. And then we also have the heat being generated times the volume. Okay, I'm indicating that as the volume. So this is specified, this is specified, this matches the exact solution. The implication is that energy is conserved for the bar. So the energy is conserved in aggregate, and this is when I'm looking at the energy coming out calculated using the discrete equation. That's the equation from the weak form. So energy is conserved in aggregate, but that doesn't mean that it's conserved for each finite element or it's conserved for each infinitesimal element. And when we go into ANSYS, we'll do a 2D conduction problem, and we'll see how these ideas can be extended to 2D, to the 2D case.